2009, number 6. If it's a number 6, good chance it's a sequence series problem. Alright, the Maclaurin series for e to the x is this. We knew that. The continuous function f is defined by this crazy thing. Now you got to think we're in series manipulation mode here, so we're probably going to be finding the series for this part and then like doing some manipulation with that. But this thing right here could be replaced with a series. When x is not equal to 1 and f of 1 is equal to 1. Function f has derivatives of all orders at x equals 1. Alright, so write the first 4 non-zero terms and the general term for the Taylor series for e to the x minus 1 squared about x equals 1. Now, you don't have to do this from scratch because we have the e to the x series, so this is just e to the something else. And the fact that it's about x equals 1, that shouldn't bother you at all. Whether you like it or not, this is a series about x equals 1 because it's got the x minus 1 in there. So that's already taken care of. You don't have to do anything to make it happen at x equals 1. Alright, so that means I'm just, everywhere where I see an x in this series, I just have to plug in x minus 1 squared. So that's going to be 1 plus x minus 1 squared plus x minus 1 to the 4th over 2 factorial plus x minus 1 to the 6th over 3 factorial. And then in general, I'm just plugging in that, so it would be x minus 1 to the 2n, right, because of the squaring and the n, over n factorial. Right? Part B. Use the Taylor series from Part A to write the first 4 non-zero terms in the general term of the Taylor series for f, that's this, about 1. Well, let's do that. Let's just work with this and see what happens. So our series is 1 plus x minus 1 squared plus x minus 1 to the 4th over 2 factorial, and so on. Minus 1 over x minus 1 squared. So you see, all I did is I replaced the series that we know for this, for that piece of that, for this function, that piece of the function. So 1 minus 1, those cancel out. And now I'm dividing through every term by x minus 1 squared. So x minus 1 squared knocks off both of those and makes that 1. It knocks this down to oops, that should have been 4th. It knocks that down to x minus 1 squared. It knocks this down to x minus 1 to the 4th, and so on. So what are the terms? 1 plus x minus 1 squared over 2 factorial plus x minus 1 to the 4th over 3 factorial. You could write out another one if you need to, but I think probably you can see the pattern. Factorials are ticking up by 1. These are going up by evens. So that's x minus 1 to the, I'm going to call this n factorial on the bottom, starting at 1. And that means that this was to the 2n. But if I plug 1 into this, or maybe I could do, well, there's 2 ways of doing this. I guess we could do, I could either make this an n plus 1 on the bottom for the factorial and start at 0, or I can make this 2n minus 2 on the top and start at 1. And I don't really think they need you to do this, but I would write that there just to be sure if you did that. So you could make it that, and you just check to see if we start at n equals 1, that's going to give me that to the 0 power over 1 factorial, that's right, and then if I plug in 2, that's going to give me the right second term. So that looks good. Or we could have done x minus 1 to the 2n, or n minus 1 factorial, and that starts at n equals 0. Those are the two ways you can do that. All right. Part C. Use the ratio test to find the interval of convergence for the series that we found in B. So we need our general term to do that. So that's the limit as n approaches infinity, excuse me, of the n plus 1 term when I add 1 to this, just turns into n, right? Divided by the n term right? That's going to leave me 2n, that's 2n plus 2, so it's going to leave me a couple of extra x minus 1s. Those can come out of the limit because they have nothing to do with n going to infinity. And then here I have 1 over n. I'm going to cancel these factorials out. Right? This is n times n minus 1, and so on and so on, so that cancels out with all those. And the limit as n approaches infinity of 1 over n is 0. So that's x minus 1 squared times 0. And that's always in between. What values of x make x minus 1 squared times 0 in between negative 1 and 1? All values of x, because when you multiply by 0, that's going to be 0. So it converges everywhere. That's what that means when you get a 0 in there. It means it converges everywhere. That's nice. Don't have to check the endpoints. D, use the Taylor series for f about x equals 1 to determine whether the graph of f has any points of inflection. All right, well, let's see. To find a point of inflection, we'd have to look at the second derivative. So I'm going to find the first derivative first. So let's take a look at this. First derivative, that's just going to be 0. This is, multiply the 2 out to the front, it cancels that out, and that gives me x minus 1 plus 4x minus 1 cubed over 3 factorial plus 6x minus 1 to the 5th over 24, 4 factorial, and so on. That's probably enough to be able to see what's going on. And then the second derivative is 1 plus 12 times x minus 1 squared over 6 plus 30 times x minus 1 to the 4th over 24, etc. So are there any inflection points? Are there any things that you can plug in that make this equal to 0? And I don't think so. Actually, the answer is a very conclusive no, because f double prime is always greater than 0 for all x. Let me tell you what I'm looking at to see that. Here's a 1. Here's something squared. Here's something squared. Or, sorry, to another even power. Even power, even power. All the powers are even here. So these are all positive, positive, and positive forever. At the very smallest, they could be 0 if you plug 1 in, but then you still have the plus 1. So you don't even have a chance of getting the concavity down to 0 is the thing here. So that's always positive, so no inflection points. Cool.